Okay, this is a walkthrough for the Work and Energy Lab, and this lab is pretty straightforward. What we're essentially going to do is we're going to take a cart, we're going to prop it up on a ramp, which is going to be the tracks we've been playing around with, and we're going to do some work as we drag the cart up the ramp. Then what we're going to do is we're going to calculate the potential energy and say, gee whiz, look at that, the potential energy looks a whole awful lot like the work. Then I have you go ahead and lift this thing straight up and say, wow, look at that, the force got bigger, the work remained the same, and the potential energy remained the same. And lastly, we're going to allow the cart to go down the ramp, and we're going to calculate the kinetic energy at the end of the day and say, wow, look at that, the kinetic energy looked a whole awful lot like the work. So here's what we need. We need a cart, we need a meter stick. I'll show you where those guys are. They're in the front of the classroom up against the wooden table. You need the tracks that we've been playing around with. We need a scissors jack that is about shoulder level up on the shelves, motion sensor and force sensor you're all familiar with, computer with Logger Pro, and a little teeny tiny bit of string. Here's a quick little simulation of what we're going to do. We're going to have a cart. In this case, the mass of the cart is 2 kilograms. You're going to measure the mass of your cart, and here it's pretty straightforward. We have a nice pretty angle of 30 degrees, and we're going to lift it to a height of 1 meter. You can kind of see that the force is 9.8 newtons as this thing goes up the ramp, and we drug it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tick marks, so that is going to be 10 times 20 centimeters is 2 meters. What we can kind of do is we can kind of go ahead and calculate the work and the energy that was gained. We could say that the work is going to be equal to the force that was applied multiplied by the distance it was applied over. It was 9.8 newtons applied over a distance of 2 meters, so we're going to get 19.6 joules. We can say how much potential energy did this thing gain. The potential energy is going to be the mass of the cart multiplied by gravity multiplied by the height that the cart was drug up, and the mass of the cart was 2. The gravity is going to be 9.8, and it was lifted to a height of 1 meter. And wow, look at that, that works out to 19.6 joules. Gee whiz, this is a simulation, and all worked perfectly well. It's not going to work nearly as well for you all, but it's going to be close. So what we can do is we can actually come back to the simulation, and we could lift this cart straight up. In this case right there, gee whiz, look at this, the force goes up, but if we were to calculate the work and the potential energy, they're going to be the same. So this is what it's going to look like more for us. What we're going to do is we're going to prop this up using the scissors jack. That's what those guys look like just right there. The motion detector is going to come into play in a little bit, so hold off on setting it up just like that. We are essentially going to say that we're going to have no potential energy right here, and we're actually going to start with the cart kind of in this region right there. So it's actually going to start off with a little bit of potential energy and a little bit of height. When you measure these guys, try to go for about the center of mass of this cart. So we're going to say the cart behaves as if all the mass is in the center of it. So you're going to measure that distance. You can use the tracks meter stick to do that, and you can measure this distance right there. You're going to use a meter stick to measure that. The meter sticks are at the end of the wooden table, kind of in a PVC pipe. They're kind of hard to miss. Then what we can do is we can measure the force using the force sensor, and to do that, what you're going to do is you see the force sensor right there. You're going to use a little teeny tiny bit of string to connect the force sensor to the cart, and the reason why I'm going to have you do that is because I want you to apply the force in the proper direction. In this case right here, you can kind of see that I'm actually not applying the force entirely in the direction of the movement. I want you to apply the force in the direction of movement, and the string is going to help you do that. Now, you actually don't need to drag the carts up. In fact, that is a little bit more difficult. All you really need to do is hold it there, and you can convince yourself that since the acceleration is equal to 0, whether you're going up at a constant velocity or whether you're dragging it up or whether you're just letting it sit there, more or less the force that you're going to measure is going to be the same. You do need to zero the force sensor, and you don't actually even need to have the software running. You're just going to go ahead and read the force off there just like you did on the previous lab. At that point, it's pretty straightforward. You're going to drag, or you pretend like you drag the cart up to this distance just right there. You can go ahead and you can measure the distance right here. You can measure the height, and again go to the center of mass of the cart. Then it's pretty straightforward. You're going to calculate the potential energy that the cart gained, and you're going to calculate the work that was done. You're going to do the work the same exact way: force multiplied by distance, mass, gravity multiplied by height. Now this is where you're going to fill all that stuff in. You're going to put the mass of the cart right there. You're going to measure the initial height, and then you're going to calculate the initial potential energy. Again, just mass, gravity times height. You're going to measure the initial distance just right there, and then you're going to record kind of the average force that you applied or would have applied. You're going to measure where you finished off at, and then just take x2 minus x1 to get your distance. The work is just going to be the force multiplied by the distance. You're going to record the second height, and you're going to say mass times gravity times height. Calculate the change in potential energy, and wow, look at that, they were roughly the same. Energy is always going to be conserved, so if these numbers are not very similar, then we should be talking. Then what would happen if we were to lift the cart straight up from H1 or from H2 to H1? Go ahead and verify that. Calculate the work. Gee whiz, look at that. Energy is conserved once again. Now what you're going to do is you're going to stick the motion sensor on the top, and you're going to place the cart where you kind of finish it off at. Then what you can do is you're going to release the cart, and you can use the examine tool, Control E, to record the velocity of the cart just after it hits the bottom of the ramp. When it comes to doing this part of the experiment, I'm going to have little teeny tiny pieces of foam, and you're just going to stick that at the bottom of the ramp to kind of soften the blow, because if you were to allow the cart to hit that directly, then, well, bad things are going to happen. What you can then do is you can calculate the kinetic energy, and you can say, wow, look at that. The kinetic energy looks a whole awful lot like the change in potential energy. If there's any discrepancy, what accounts for it, and you can do this part on your own when you get home.